Welcome to Rust for Windows, the series for Windows developers wanting to learn how to make the most of Rust on the Windows platform, otherwise known as the series for Rust developers wanting to learn how to make the most of Windows with Rust. My name is Kenny Kerr, and in this third installment, I'm going to introduce some more of the individual crates published as part of Rust for Windows. In Part 2, we examined the Windows and Windows Sys crates, among others, and how they provide access to virtually all the Windows APIs, whether you are looking for WDK, Win32, C-Style APIs, COM APIs like Direct3D, or even WinRT APIs. If you're not sure what you're after exactly, that's probably a good place to start exploring APIs and features on Windows. But those monolithic crates have some drawbacks. They're quite large and they are necessarily generated from metadata. So there is only so much they can offer in terms of safety and ergonomics or an idiomatic programming model familiar to Rust developers, not to mention practical versioning stability. Enter some of the more focused and hand-authored crates that provide access to very specific APIs and programming models. These are tiny in comparison and provide highly tailored experiences for efficiently, safely, and naturally using the various Windows-specific APIs. While they are built on the same metadata and code generation facilities as the Windows and Windows Sys crates, they don't themselves depend on those larger crates and are thus very streamlined and lightweight from a dependency perspective, ideal as library crate dependencies. The Windows Registry crate provides simple, safe, and efficient access to the Windows registry, whether you need to simply read a quick value or manage a transaction of registry changes. The Windows Services crate makes it super easy to build a Windows service in Rust, typically a long-lived background process that runs outside the context of an interactive user's logon session. The Windows Version crate provides reliable operating system version information without the need for application manifest files or other trickery. The Windows Threading crate provides simple, safe, and efficient access to the Windows threading support. While the Rust standard library has great synchronization primitives, actually creating and reusing threads efficiently is a uniquely challenging problem on Windows, and this crate makes that a breeze. And the last crate we'll examine in this video is the new Windows Link crate that replaces the older Windows Targets crate, but more on that in a moment. Let's head over to VS Code and take these crates for a spin. First up, let's explore the Windows Registry crate. Start by adding the crate dependency. And in the main source file, we can immediately begin to interact with the Windows registry via this handy crate. The use declaration is just a convenience, and will employ result-based error propagation for simplicity. How about a simple example? Let's get the product name for the currently running version of Windows. And we'll dig into the local machine hive and open a subkey. Software, Microsoft, Windows NT, and current version. And finally, read the product name registry value. And let's print it out. And it looks like I'm running Windows 10 Enterprise. Well, I'm actually running Windows 11 Enterprise, but then this isn't the best way to figure out which version of Windows you're running on. That's what the Windows Version crate is for. More on that in a moment. Let's look at a more interesting example for both reading and writing registry values of your own. You can, for example, use the create method to create or open a registry key for read and write access as follows. That's just the path to the registry key and the key itself. Now what if you only want to open the key if it already exists? Well, you can use open instead, but it offers only read access. This is where the options method comes in handy. The resulting open options type is modeled after the standard library's file system open options, as it provides options and flags that you can set in order to configure how a registry key is opened, something like this. And let's set a value. So this opens the subkey with write access, but only if it already exists. Sure enough, it doesn't exist. The call fails as the key does not exist. Want to create the key in all cases? Just set the create option. And let's give that a try. Yay! You can also optionally create a transaction object for transactional access to the registry. And let's just make this a bit more readable. Sure enough, that works as well. The important thing with transactions is to remember that you need to actually commit them. Failure to commit the transaction will cause all changes to be rolled back when the transaction object is dropped. They are also not observable outside of the transaction until and unless commit is called. That's better. There's plenty more there for registry access, enumeration, and handling different types of values. We may have to do a deep dive into the registry in future, but let's now move on to the next crate. The Windows Services crate is just as easy to use. It shouldn't be hard to write a Windows service, but if you've ever tried using the raw APIs, you'd be forgiven if you thought it was incredibly hard. Let's add the crate dependency. And the use declaration. The Windows Services crate provides a super simple service type that lets you write a robust Windows service with minimal boilerplate and no unsafe code. Not unlike the Windows Registry crate, the Windows Services crate offers a service builder pattern to set the commands you wish to support. Let's support the stop and pause commands. And then it's time to run the service. You just need to give it a closure that will be called with various commands as they are sent by the Service Control Manager. And that's literally it. Let's take it for a spin. So obviously we'll need to inspect that command variant, but for now let's look at the output that running the service produced. A Windows service cannot be run from the console. It must be installed and started by the Service Control Manager. And the Service Builder helpfully prints out a few commands to help you install and test your service. For that we'll need an admin console. We can start by copying the install command. Great. Service created. And then you can start the service. And there you can see that it's running. You can even bring up the services snap-in and find your service there. Sure enough, there it is. And you can see that it's running as the local system account. And let's stop it. And back in the console, we should be able to tell that it stopped. Sure enough, there it is. Okay, so just to illustrate that the closure is being called, let's do some very rudimentary logging. We'll just create a simple file. And for diagnostics, let's just write out the commands as they are received. And we need to rebuild the service. And then we can start it back up in the admin console. And let's bring up the log file. And there you can see it started. So let's pause it. And sure enough, it received the pause command. And then resume the service. Yep. And finally stop it. There you go. And sure enough, you can see that the Service Control Manager calls the closure for each state change. Again, much more to be said about Windows services, but that should get you started. And we'll move now on to the Windows version crate. Back in the cargo toml file, we'll add the crate dependency. Now remember earlier we looked at how you can get OS information from the Windows registry. But if you really want to know what version your app is running on, then the Windows version crate is just the thing. In the main function, the use declaration, and now we can print out the actual version of Windows I'm running on. Let's see. So the actual major version has no real meaning any longer. What matters is the incremental nature of the version information. Specifically, things like the build number, and whether a given OS feature is available so that you can programmatically light up various application features based on the availability of certain OS features. How? Well, something like this. You see, the OS version struct implements version ordering, so you can easily check whether the current version is greater than or equal to some known version. And if that's the case, we can use some widget. Let's see. We can. That's great. And closely related to versioning is whether your app is running on the client or the server version of Windows. And let's give it a try. So sure enough, I'm running a sufficiently current version for that feature, but I'm not running Windows Server. And that's all there is to it. And that's certainly not the only way to implement feature light-up on Windows, but for some features and APIs, or workarounds, that's really the only way. The next crate in today's tour is the Windows threading crate. And that's the dependency. And the use declaration. Here is how you might submit a closure to run on the default thread pool. This might appear similar to the standard library's spawn function, but that always spins up a new operating system thread. Here, the closure will always be queued up for the default thread pool and not add any unnecessary scheduling pressure. For the sake of this example, we'll just put the main thread to sleep indefinitely. Both sleep and submit are functions provided by the Windows threading crate and map directly to the underlying threading support provided by the operating system. And so is the thread ID function. And let's print out the pool thread ID as well. And then let's pretend to do some work. And sleep for a while. Alright, let's take that for a spin. Cool, so you can see the execution switches to the pool thread while the main function sleeps indefinitely, but at least keeps the process alive. The submit function is useful as a building block for higher level threading abstractions. For example, it's used to implement Windows async futures. Perhaps a more directly applicable function provided by the Windows threading crate is the parallel for each implementation. Great for fork join concurrency, crunching data in parallel. Let's use a reader-writer lock to illustrate. And then we can just call for each with any iterator. In this case, the closure will be called on each element produced by the iterator, in parallel, using the Windows thread pool, and then wait for all closures to finish executing. This is typically far more efficient than custom or third-party schedulers, as this is backed by the Windows kernel itself, so it's careful not to overschedule the available CPUs as it orchestrates work from multiple processes. And let's print out the thread ID as well as the current value. We can then retrieve a write lock. And update the counter. It's kind of like a parallel sum algorithm. And then finally, we'll print out the results. Alright, let's see if I got that right. Nope, there's a typo. One more time. There we go. So as you can see, the thread pool doesn't just go and spin up a thread for each iteration. No, it tries very hard to reuse available pool threads for efficiency. You can better visualize this distribution with the pool object that the for-each function uses under the covers. Let's use another reader-writer lock to collect stats. And then we'll go ahead and create a pool object. You can even set minimum and maximum limits on this new thread pool. The min threads, 2 in this case, guarantees that at least that many threads will be created, while the maximum, 10 in this case, prevents the operating system from allocating more threads even if more cores are available and idle. Failure to call set thread limits just means you're leaving it up to the operating system to figure out things, which is usually a good default. So let's submit some work. Previously, we used the default submit function, submitting closures to execute on the default thread pool. But this submit method will specifically target the private threads belonging to this pool object. Another handy consequence is that you can easily wait for all of these private callbacks or closures to complete. The join method will wait for all submissions to finish executing. Dropping the pool will also wait for all submissions to finish, as the closures cannot outlive the pool on which they run. Okay, let's grab a write lock. And update the hash map with some stats. Here we're basically just incrementing a per thread counter to see how many callbacks are dispatched to each available pool thread. And let's print out the results. Alright, let's see what that does. Interesting. So all but one of the callbacks were serviced by the same thread. What gives? Well, again, as I mentioned, the scheduler doesn't want to spend extra time scheduling different threads when it can more efficiently run very short-lived work items on a single thread. Can we prove this? Sure. Let's add a tiny delay and see what impact that has. And let's try again. That's better. So just that tiny sleep is enough to compel the scheduler to put a few more threads into action. Obviously, you'd never want to actually sleep in this way. Just think of the sleep as some actual work or data crunching that you're doing in real life. Knowing that the operating system can sense when threads are actually busy and forward progress needs to be made, and can be made by dispatching submissions to other available cores. So here, for example, we can also see the thread limits in action. If we were to limit the pool to exactly 2 threads, and running it again, sure enough, the operating system will distribute work to only those 2 threads. Okay, again, very simple, safe, but really convenient to harness the power of Windows efficiently and effectively in Rust. No extra redistributables, runtimes, or large dependencies. No, this is just you and the operating system. And the final crate we'll sample today is the new Windows Link crate. Previously, the Windows Targets crate provided support for linking or importing Windows APIs or importing Windows API calls statically into a Rust binary. The Windows Targets crate depended on redistributing per architecture and per compiler or toolchain specific import lib files, rather large ones, that described to the target linker which library to load and how to resolve a particular function in that library. As of Rust 1.71, this is no longer required, as the Rust toolchain can directly generate the necessary imports given just the library name and function signature. It does, however, do this in a rather convoluted way, so the Windows Link crate steps in and provides the convenience of the former Windows Targets crate and its link macro, but based on Rust's new raw dylib feature. Something like this. kernel32.dll, the system calling convention, and the getCurrentThreadID function, returning an integer. And as you can see, this looks exactly the same as the old Windows Targets crate, if you've played around with that or seen the previous video. The only thing that changed is the crate name, but you benefit from not having to download all of the big lib files. The Windows Link crate will be careful to translate this into the Arch-specific incantations needed to resolve the import. And there you go. Now obviously this will be simpler and safer just using the Windows Threading crate, but you can obviously see how this extends to whatever functions you need to import. So that's the thinnest Rust for Windows abstraction, and undergirds virtually all of the other Windows crates. And now thanks to Windows Link, none of them have to depend on large target-specific import lib files. Another benefit is that since the pre-generated import libs aren't used, there is no need to limit the link macro usage to only those APIs that were known at time of publication. Indeed, you can use it to import and link functions from any third-party library as well. So whether you prefer using the Windows, Windows Sys, or one of these more targeted crates, Rust for Windows has you covered. But there's much more to discover and learn about Rust for the Windows platform, and we'll explore it all in due time. So stay tuned for more in this series on Rust for Windows. Until next time.